Joining us today at our Light Sources and Luminaires class. My name is Armando Verdiel, Technical Development Supervisor for Lighting Design Lab. And today's presenter is going to be Eric Strandberg, Senior Lighting Specialist. Again, great fundamental class, great to get a solid understanding of many lighting topics, how to measure light, legacy technologies, as well as LEDs. So a lot of good stuff coming your way today. Next slide, please, Eric.
Stand by.
There we go. Just everyone should be well aware of our operations, but we're going to go through them very quickly. You'll know that everyone is muted, but please engage with us. At the bottom right-hand side of your GoToWebinar dashboard is going to be a chat option. You can enter comments, questions, or anything you'd want us to address. I'll be managing that, so please engage with us. It's always useful when you want to elaborate on a certain topic. We'll be stopping periodically to answer questions or address comments. Just as well, we're going to have a few online polls just to make sure we're getting the great information across. So please participate in the polls. Those are good. Those are fun. After the webinar, there's going to be a very short half-a-minute survey of how we did. Please answer it. It does help us understand how to improve our experience for our audience. And as always, a recording of this session as well as the slide deck is going to be available on our webpage in our resources tab and our education tab. As a note, Lighting Design Lab is a department of Seattle City Light. We are powered by Seattle City Light. Same entity. Is always want to make sure that we carry that across. Next slide, please. Interesting. Wanted to note, I'm just seeing the slides still transition, that Lighting Design Lab, we love to work with the entire market industry as we are providing solid awareness and education on connected lighting topics, as well as now we're also branching out to electrification topics. But we also work with trade allies, your contractors, utilities, retrofit organizations, ESCOs. We work also with design allies, your architects, lighting designers, building engineers, and also with end users, your building operators or facility professionals, and ensure that we grab information from each one of these audiences and are able to disseminate what we learn and ensure that everyone is in the same page as we try to get our buildings smarter, more efficient, and ultimately better for the people in them. Next slide, please. And again, our 4 core service areas, we do education and training, like our webinar series that has been going on since early 2020. We do technology evaluation and demonstrations where we pilot technologies, do some research, and are able to disseminate the findings. We develop tools and resources, such as network lighting control best practice guides. We have a luminaire level lighting control resource video, and you'll find many other lighting guides and resources on our website. Lastly, we serve as information aggregators. We keep our ears close to the ground to the latest and greatest on conferences and the lighting industry and beyond, and are able to then curate good information to share with our audience. Next slide, please. With that, I leave you all with Eric. Take it away, Eric.
Thanks, Armando. Really appreciate it. And I want to thank everybody for attending this this webinar. Lighting design really starts in the mind of whoever is making decisions about lighting. And that could be a lighting designer, it could be a building operator, it could be a contractor. But regardless, you have to have good ideas. But no matter how good those ideas are, if you don't have an understanding of some of the basic tools of lighting, light sources and luminaires in particular, it's going to be very difficult for you to implement those ideas in a way that's going to be fruitful. So one of the things I love about lighting is there's always something new to learn. I know some of you are maybe brand new to the industry, and welcome. And this will be your first lighting class, but believe me, it won't be your last. I love the fact that I'm always learning something new. And, I've been at the lab for a long time, and teaching about lighting is something that I really enjoy because I have a passion for lighting. It's crazy, I know. But one of the things we're going to look, some of the things we're going to look at today are basically, as we said, light sources, some of the ways that we communicate details about light sources, look at some of the luminaire families. They're not all the same. Even some that look similar are actually different. Different tools. Talk about photometry, how to understand some of the literature that you'll encounter, and then look at some, how the specifications are put together. And again, we could teach an entire week on all of these topics, and so we're gonna kind of plow through some things, hit some high levels. We'll have the little quizzes as we go, and I think if you have questions, put them in the chat, and we'll either try and get to them at the end, or Armando will be monitoring those, and if it seems like it's something relevant or at least topical, we might get to it as we go. So yeah, I mean, one of the best ways to learn about lighting is by seeing, and that's, again, one of the things I love about it is you can see it all around you, no pun intended, but, we're very visual creatures. And so I look around and I see lighting, good lighting and bad lighting and indifferent lighting. And, there's just all different kinds, and you can learn as you go. And just because you see lighting in a nice fancy building doesn't mean it's actually good lighting. So pick up what you can, and try to learn from others. So this little slide is based on a slide from the IES, the Illuminating Engineering Society. And I've tried to modify it a little bit with some different images, but basically they've broken out, the four basic parts of vision and perception and light, and I think they've done a pretty good job with it. And certainly lighting starts with light sources, and those can be natural light sources. The sun certainly is primary. And then there can be some like flames and things of that nature that are either natural or man-made. And then, of course, we have electric light sources. And, of course, that's what we're going to focus on primarily in this class. And there's all different kinds. Even with the LED revolution, as it were, there's still a lot of nuance and differences between various LED light sources. So we have light sources, but honestly, it's pretty rare that we're actually looking at light sources, because it's usually too intense, unless it was birthday candles or something. But if we're lighting architecture, we're not looking directly at the sun. We're not looking directly at lamps. So we have modifiers of different kinds that we use in the built environment. We have glass of different types where we try to change the light as it enters buildings. We have electric light sources here that are, in this case, they have a lens of, a shade, we call it. Light sources there. We have light bouncing off of surfaces. That's another common way to bring light into a space. We're not seeing the light source, we're seeing the light reflected off of a vertical surface. Water, all these different things modify the light to make it more suitable for human perception. And then, of course, we have the eye and, the receptor. So light enters the eye. and there's a mechanical process that goes there. But then there's the brain, and it could be argued that that's where lighting happens, actually. How we interpret the source as it travels and comes in to our consciousness. So we'll see maybe a little of that as we go. So again, this isn't really a physics class, but what we call light is generally the visible portion of a much larger group of electromagnetic radiation of all different types. And then, so we have visible light. And in the lighting profession, we do need to be cognizant of the edges of the visible spectrum. We call it infrared light and ultraviolet light. And ultraviolet is not generally perceived, but it is part of something that the lighting designer needs to be aware of. In many cases, we're trying to minimize or eliminate ultraviolet light completely, whether it be a museum or maybe we're using it lately. We're hearing a lot about ultraviolet light in terms of keeping spaces, cleaning the air, cleaning the environment from pathogens. Infrared, we have sensors that we use for controls that use ultraviolet, the infrared occupancy sensors in particular. Yeah, again, this isn't a biology class either, but light enters through the iris, it goes through lensing, and it hits the back of the eye, the fovea, and there's light sensitive elements back there. Generally speaking, we call them rods and cones. I'll caution you that lighting is, especially when it comes to biology, we're learning new things all the time. And so, the idea that there's just rods and just cones is maybe not, that's for this sort of high level, that's probably good enough. There might be somebody out there who's studied this, as you can say, well, there's other things, and that's true. And even, generally we've talked about the rods are for primarily light and dark. We have a lot more rods, and then we have a concentration of cones in the back of the eye that we use primarily for color perception. And the cones, we've historically broken into sort of three groups, ones that are sensitive to blue, green, and red, and those are happen to also be the primary colors of light. We'll touch on that a little bit later too. As we learn more, we're finding out maybe there's only the cones are different. But for this class, we have the rods and cones, and that's how light enters or is stimulated to the nerves and enters to our brain. But we're always looking for patterns. Humans are constantly trying to make sense of this world, if you will. And so we have light and dark entering our eye, and we're trying to find meaning in that. I mean, not necessarily just specific, we're trying to make sense of it. So we can have other patterns of light and dark. So here's this light and dark, and it's just sort of chaotic, and there's maybe nothing there. But it doesn't take a lot for us to maybe start to perceive something in that light and dark. Most of us can see a dog standing here, maybe with his nose to the ground. So there's just hardly anything there telling us that that's what that is. But that's what brains do, is they want to find patterns. They want to make sense of the stimulus that comes in. So, and again, we could spend a whole class on this sort of thing, but we're just going to kind of, I guess the idea is that that's where where given, where vision actually takes place, that could be argued is in the brain. All right, but back to electric light. Well, any light source really. Light sources we try to sort of group together and separate into different types. Broadly speaking, regardless of whether it's a natural light source or a electric light source, we look at, are they point source, a linear type source, or a planar type source, and we'll touch on that in a second. So we're curious, when we're doing lighting design or selecting, making choices, we're picking them perhaps based on this, at least as a starting point. Then of course we're concerned with the intensity. How bright are they? Some are inherently much brighter than others, and we kind of characterize that as their lumen output. We'll touch on that. Then there's the efficacy. How much work do we have to go through to get light from that source? And of course, if we have to put a lot of energy into it and not get much out, then that maybe isn't as good as something that takes less effort, less energy. Then we look at the life of the light source. If we're constantly having to maintain it, that may just be the fact, but if we found something that has less maintenance, all else being equal, we would want that. I mean, there was a time when all we had were candles, right? And they were constantly burning out. You had troops of people going around changing candles. So we've come a long way, I think. Then we have correlated color temperature, or basically the color of the light. Is it warm or cool? And then how well does the light render the true color of objects? So those are the big categories, and we'll try and go through some of those. So a point source, one of our best point sources, most common, is sunlight, and it comes through and leaves these hard shadows. Point sources add drama to a space. They can really highlight something, and then we have darkness other places, and things pop out. And so typically they can be easily focused, and we can shine a spot. One of the things they have is shadows. I'm going to try and do this little demonstration here. Bear with me. Everything's backwards on my screen. So, but if you look here, you can see my shadow, and it's fairly crisp, right? So that's a point source. It gives a hard shadow. Let's see. I think I had yeah, there we go. We'll look at another one in a minute here. So they do create interest and sparkle. For that. Then we have linear light sources. That would be, a slot of some kind in the architecture that might allow light to just pass in a certain controlled manner. We can do coves of different kinds and add, maybe this helps in something like wayfinding, or directing people into space, or defining an architectural environment. And they tend to minimize some of those shadows that we were talking about earlier. And so that's another tool. And then lastly, we talk about planar light sources, and sometimes they are really just a result of a modifier, right? So we have a skylight. So if we go back, I won't do too much here, but here we have clear skylights and we get this direct beam. But if we have a diffuse skylight, we get very diffuse light coming from even direct sunlight. Indirect electric lighting. So we have these linear pendants shining off of a ceiling, and then we'll look at a fairly new light source that is in fact actually planar, the OLED. But when we have too much indirect light, you get a very diffuse, shadowless environment. You just like the point source can give us high stimulation, drama. Too much of the indirect lighting, in fact, I used to call it the cloudy day effect. If it was done perfectly, it's almost minimal stimulation. It's almost, a case where, it's too diffuse. And it's pretty rare that you're doing only one type of lighting. It's pretty rare that you do only point sources, or only indirect shadowless light. Usually you're adding some other sort of accent lighting. So, yeah, so those are our things there. All right, so let's
have a first polls here. Awesome, Eric. Let me go ahead and grab it. All right, everybody, which of the following are lighting modifiers? Please select all that apply. A reflector, the moon. Can a wall be a lighting modifier? A green candle, or the octave nerve? Thank you for those who started voting already. Votes are coming in, so thank you. The more engagement we have here, the better. More enjoyable the experience is for overall. I'm gonna keep it open for 3 more seconds, 5 more seconds. All right, let's close this here. We're gonna go ahead and share.
Great.
So we see a reflector got the majority of 88%. We have the moon at a 64%. A wall, another 88%. The octave nerve had a 27%, and the green candle had 6%. Eric, any comments on that?
Well, yeah, and in fact, thank you for everybody who voted for the moon. I was going to talk about it earlier, and maybe in my excitement I forgot. But yes, right. So the sun, is a source, but moonlight is reflected off of the moon. Is sunlight reflected off the moon. So yes, the moon is our big modifier. A green candle, yeah, that was a little bit of a right. It doesn't matter whether it's green or red. It's still a point source, a source. So, and the optic nerve really isn't a modifier, although maybe some could argue that it, it's all getting modified there, but not really. So that was kind of a great. So I think you all got it. Appreciate the input there. All right. So we talked about, the shape of the light a little bit. Let's talk about intensity, and there's, lots of ways to describe that. But the basic thing that we think about when in the lighting community is the lumen. And that is just the total amount of light emitted by a light source. And bear in mind, that doesn't necessarily mean that's the amount of light that's hitting what we want the light source to light. It's just the total amount coming from that light source. And so we have our light source maybe in this virtual or sometimes a real sphere. We'll talk about that measurement later. But we have our light source, and then as the light source travels, maybe outward, maybe a meter, let's say, in the case of or even a foot. It would just depend on whether we're doing in this country we do feet, but in the most rest of the world we go at a meter, and so we have our candela coming out, and so that would be a meter there. And so sometimes we talk about candelas per meter squared. So yeah, and we'll touch on that here in a second. When we have a directional light source, let's see here if I can do this. We, not all the light. So here we've got our little spotlight, and we can see that it shines up, and most of the light comes out in a pattern, but there's some light that comes out to the sides and in other places. So, but usually what we're talking about with directional light source is a beam angle, or the beam. Sometimes we'll just talk about it. And so how to describe that? You know, we can have a light source that is a spot, a narrow beam of light. We can have a light source, a light that is a flood, a wider beam, and then sometimes you know, it'll be something in between, a medium beam, let's say. And those are they can be those sorts of designations can be handy when you're just casually talking about lighting, maybe on a project, or say, yeah, we need a spotlight here because it's a long distance, or we want to focus the light, or let's flood this. Let's use floodlights. But that's not very exact. So typically we want to have something more precise, especially if we're doing calculations. And so we have the beam angle. And the beam angle is the angle at which the light drops to 50% from the center beam candle power. So we'll be given, usually in our spec sheets, they'll tell us what's the center beam candle power. And then they'll tell us maybe what the beam angle is. Maybe it's 30 degrees or something. But bear in mind, that's not all the light. And so sometimes you can get glare, or you can get unwanted light in places, because there's going to be a field angle, and the field angle is where it drops to 10%. So you're going to have a certain amount of light that's going to go outside of that beam angle. And, you know, you may need to control that, or maybe you don't, that maybe it doesn't matter, but it's good to be aware of that, because often that stray light, as I said, can be glare. Let's see here. So let's put some of this together. You know, we'll introduce a few topics. It's hard. Lighting is one of those things where there's so much to know. It's hard to, you know, it's hard to get all the information out in a consistent linear way. But we'll just talk about a few things that we've already touched on. So here's our light source in a light fixture, and it's giving out lumens, right? We talked about lumens from our light source. And so the light comes down out, you know, usually in a uniform pattern, although not always, and it strikes a task area, let's say. If we were to measure that, take say a light meter, we would either measure foot candles or lux, depending on how we had our meter set up and maybe which country we're in, or maybe even which century we're in. You know, foot candles is historically been used in this country. Lux is becoming more and more. It's the metric version that's used in the rest of the world. You know, so there it is. But so we think we've got it all figured out. We put our light meter down and we measure foot candles, and that's the light, right? But as I said, you know, lighting actually happens someplace else. It happens in the eye and in the brain. So we're not really interested in how much light shines onto a surface. We're interested in how much light reflects off of that surface into our eyes. And so we have illuminance striking a surface, and we have luminance reflected back, brightness. And we measure that in candelas per meter squared. Or this is hardly ever used anymore, but you may see the term foot lamberts. Again, that's the equivalent of sort of a foot candles. Foot candles still is used. Foot lamberts is almost never used, but you may run across it. But it's candela per meter squared or luminance. So we think we've got it figured out, right? So that's easy. But guess what? If we change things in the environment, like the nature of the task, it's the same amount of light striking that surface, but now we have a very different visual experience and very different amount of light reflecting. We'll just go back here. Keep your eyes on this little task, and you can see. So it's not even as simple as just how much light is striking the surface, or how much we have to know something about the nature of the task to really understand whether something will be glary, whether it'll stand out as a contrast in an advantageous way. Lots of stuff you can find. The IES, the Illuminating Engineering Society, has their definitions and that's actually online in a new document, but you can find hard copies as well. I'll warn you, they get into very scientific definitions of things. I'm trying to bring them down to an area, a level where most people can understand it. Hopefully I've been halfway successful. Let's continue on though. So we talked about the shape of the light. We talked about intensity. Another thing that comes up with light sources is what we call efficacy, or lumens per watt. So we knew about lumens. Well, how much work, how many watts does it take to get a certain amount of lumens? And for most light sources, and again, we'll look at a list here of light sources, and pretty much every one of these is obsolete except this last one. But so we'll look at these other ones briefly, and just to give you a sense. Sometimes it's good to know where you've been to give you a sense of where you are. So here's high pressure sodium. We'll touch on that very briefly later. It's a light source that's commonly used for exterior. And it has about 70 to 145 lumens per watt. So there's a range there. Metal halide, again, another high intensity discharge light source. It's got 68 to 120 lumens per watt, basically a 2-to-1 ratio in both of these cases. So, you could have a light source and it's pretty wide disparity of how much light you'll get. And bear in mind, we'll find that's true with LEDs. So forget induction. Here's incandescent though. That's a light source you'll run into. 8 to 13 lumens per watt. Yes, I did not skip a zero here. So if we look at incandescent light, or even our old friend halogen, very low lumens per watt compared to the old incumbent sources. Compact fluorescent, 50 to 80 lumens per watt, definitely much better than incandescent. Linear fluorescent, 60 to 90 lumens per watt. So we look at LED, and mostly we're looking at delivered lights, but not always, and we'll touch on that later in the presentation. But a very wide range. Probably we're not finding too much anymore that's down in this 50 range, but we're seeing numbers. Even in the lab, they're over 200 lumens per watt on LEDs. So a wide range. So be aware of that, but also very high lumens per watt. It's great. We're loving it. Again, looking at efficacy, the trends. Incandescent was a sort of made improvements, but it remained static for many years. We saw other light sources improve, but no research is really being done. No improvements are being done. LED is it, and they're improving dramatically. Rated life. Again, that gets back to how often are we going to be servicing our lighting system? And with the old incumbent light sources, incandescent would be maybe about 1,000. These are hours. We might be looking at 1,000 to 2,500 hours, depending on which it was. Very low, so high maintenance. Fluorescence. Again, a vast improvement, but compared to these LED light sources, I'm not sure actually about this 100,000 hours. It's a number we see, but and the screw-in LEDs are substantially less, but still very high compared to some of these other incumbent light sources. But how do we determine the light? Well, historically, and this will have some bearing on LEDs, what we've done is taken a fairly large sample of those light sources, and we cycle them on and off, 15 minutes on, 3 hours on, 15 minutes off, 3 hours on, 15 minutes off. And they all start out at 100%, and then as time goes on, some of them start to burn out, moral burnout. And when 50% of those lights have burned out, that is the life of that light source. Some are going to last longer, but and some won't last as long. So that's kind of how it's done, and you'll see that that's relevant here in a second. So there's other ways though that we determine life of a light. I mean, obviously, if it just stops working, we flip the switch, nothing happens. We know that. But here's a case. Sometimes we see color shift, right? So here we've got this wall that's being lit. We can see minor color shift in some of these, but boy, this one looks like a real stinker. It's still putting out light, but it's a problem. So it's lost its life, its service life. You know, we can see efficacy reductions, right? They start to age in ways that reduce light output. You know, at what point has that light source reduced its light output to the point where it's no longer doing its job? The light may become unstable. It may start to cycle on and off, you know, blinking or, you know, period intermittently. So one number that you're going to see as you go, if you're just starting out, but even some of us who've been doing this for a little while still get a little confused. This is called L70, life 70, which the point at which only 70% of the initial lumens are still being emitted, right? So we've lost 30% of the light. And the industry normally says this is the service life. That's the end of the service life. So it's lost its design ability. It's no longer lighting that loading dock edge to where it should be. It's no longer, there's a safety concern, or it's become too dull to perform its function. So all light sources lose light over time. Here we have some fluorescence, here's incandescent, another fluorescent, high pressure sodium, mercury vapor, and they all start to lose light. And here's the average rated life, some fairly quickly, some hold it throughout their life. They never hit that 30%, that L70. They just burn out before they lose their life, the light. So yeah, but one thing that we've found with LEDs is they don't actually burn out in the way that a typical light would. So an incandescent lamp, you know, after 1,000 hours, it no longer is giving any light at all. But it's not reached that L70. It's still putting out most of its light. Whereas an LED, the concern is that it'll just persist and just get dimmer and dimmer and dimmer and dimmer. And it won't be serviced. So people in the industry are wanting to know, when is that L70 gonna arrive? You know, will it be after, say, in this case, let's say 58,000 hours? That's a long time. How many hours in a year? There's 8,700 hours in a year. So that's still many years of use. But let's say that was 58,000 hours was the number. So in the specification sheet for that product, you'd see L70 at 58,000. How do they figure that out? Because that's many years. We're not doing real life testing. Remember that testing we talked about earlier, where they have a large group of them and they cycle them on and off, and when half of them burn out, that's the life. Well, we can't do that with LEDs because it's just years and years out. So we have to project that. And so we have to gather data. And in the early days of LEDs, there was all kinds of ways people were gathering data. It was kind of the wild frontier. So the industry said, okay, they came up with a lighting measurement method, LM80, and said, okay, if you guys are going to be a legitimate manufacturer and put out spec sheets that are consistent for everyone, you need to gather that data in the prescribed specific way. They're like, okay, we'll do that. But then there was a bit of a problem, because once you have data, you can manipulate that data all kinds of ways. And so they're like, okay, now here's another industry adopted method by where you have to use to calculate this data. So everybody's taking the data the same way and calculating it the same way, so that the end user, the specifier, the buyer can have some surety that it's basically apples to apples. And so we have so these are three numbers that you're going to run across: L70, LM80, and TM21. And if all that comes in, if these two are done right, you'll have some surety about these numbers. And sometimes they'll list L90. They'll say, well, we at L90 we've only lost at 10% of the light, and that may be a big number. They might say we can get to 70,000 hours, or whatever it is, and we've only lost 10% light. So you may see other numbers in there. There's one other thing that sometimes gets confused with some of these, and this is the LM79 report. So this is where all this data is gathered in terms of lumen output. It's all collected here in terms of light output, lumen output, life, color properties. So here's this, hopefully you can see it, is NAVLAP approved. So that's National Voluntary Laboratory Accreditation Program. So that means that these laboratories are using similar equipment that is calibrated to a specific standard, and so their data is going to be consistent. And so when they publish this data, you can have some surety that it is accurate. Okay, another poll. Have I lost Armando?
No, we are right here.
All right.
I don't see the slide with the poll, however, Eric.
Oh, interesting.
Yes. That's the slide.
Well, let's see.
If we go back.
Yeah, let's go back. So there.
I have the poll up, and we go, how is the beam angle of a light source defined? If you remember the center beam candle power conversation, the field angle and the beam angle. So the question again, how is the beam angle of a light source defined? In degrees, the angle at which the light from the center beam candle power drops to 50%, the angle at which the light from the center beam candle power drops to 10%. It's defined in foot candles, or it's defined as either wide, spot, or narrow. How is the beam angle of a light source defined? Thank you everyone for voting. And I'll take a second to note, is there any questions or comments? Again, please write them in the chat and we will address them accordingly. All right, we got a good amount of votes. I'm going to go ahead and close it. This is an interesting one, Eric. I'm gonna share with you. We have 42% of participants voted for in degrees. 48% of participants voted for the angle at which the light from the center beam candle power drops to 50%. 6% of the voters noted the angle at which the light from the center beam candle power drops to 10%. No one voted for foot candles, and we have 3% that voted as either wide, spot, or narrow.
Okay,
what's the verdict?
Yeah, no, the verdict is good. So some of these were correct. There was more than one that I would say is, so degrees is typically how we would define them, but and then the angle at which the light drops to 50%. Both of those are correct. And even E as either wide spot or flood. As I say, in casual conversation, you could be saying, yeah, that looks like that beam is wider than the other one, or you could say that's a narrower beam. So, you can use those terms. Depending on how geeky you are, sometimes we see people saying, "Oh, we're using 10-degree beams on our project, or we're using nothing but 25-degree beam," and that's cool too. So yeah, thanks a lot. Good call there, Armando.
Solid.
Everybody participated. So then the color qualities of the light, right? So we've talked about some of this sort of numerical stuff, but really the exciting part of lighting is visual, and color is certainly something that people are attracted to, understandably. So you look at these two; these are both considered, white light architectural sources, but they really have a very different effect. This is the same cars here are up here, and so right, why would we ever use this one? And that's actually a good question, but there were reasons. So one of the things that we notice right away with light is its color. Sometimes maybe it's not as conscious, but we're definitely affected by it. And so we have this thing called correlated color temperature. And, essentially that comes out of laboratory testing, where they take a chunk of metal, a specific type of metal, they put it in this thing called a black body radiator, which is basically just a big interior that reflects no light. And then they have a little port in there where they can measure the light, and they heat that piece of metal up. It gets hotter and hotter. Imagine it's like an oven or a toaster, where you turn you look inside the toaster or a toaster oven, let's say, and nothing's happening. When you turn it on, and pretty soon those coils that are toasting things turn red. Well, they're glowing very low color temperature, red hot. If you could really crank that oven up, pretty soon it would get white hot. It'd be a higher Kelvin, rather a higher temperature. And so we use kelvins when we talk about that. I think I have that on another slide here, but we don't use Fahrenheit or centigrade. So yeah, it's a little counterintuitive too, because we'll look at it here in a second. So for instance, we have natural things that have Kelvin that have color, like a candle is a very low color temperature. Daylight, actual daylight and sunlight, daylight changes a lot, but the industry recognized 6,500 degrees as daylight and 5,000 kelvins as sunlight. Incandescent lamps are somewhere in here. Historically, fluorescent lighting we could pick different kelvins easily. Some of the other light sources, like high pressure sodium, just sort of came one way. Metal halide had some variation, but sort of just came one way too. But LEDs could be almost any color temperature we want, and that's one of the exciting things about LEDs. Another thing that color temperature influences is our perception of the space. And some of these have to do with applications where we would typically use them. If we're doing hospitality type applications, we want these warmer colors, temperatures. If we're doing things more related to office and maybe industry, we're in these sort of more neutral. And then we get into some specified retail applications, healthcare. I recently had surgery, and boy, they wheeled me into that operating theater, and it was zingy. It was blue light. So yeah, but then we see that if you go into a retail store or a jewelry store, a lot of times they'll have blue, very high Kelvin temperatures in industrial applications as well. So nothing's perfect to one or the other, but that's generally how we do it. I will tell you too that even for the same lumen output, so two light sources, one maybe the same color, the same lumens, typically people will say that the cooler one, the bluer one, is glarier, or even brighter, they'll say. And I can't tell people that they're wrong, but because seeing is believing, but if I had a light meter, it would measure the same number. But of course, we'd light for the human eye, not for meters. Let's see, I don't know if we can see this very well. So here's a cooler light source, and here's a warmer light source. And they're both the same lumen output. Anyway, it'd be fun if we could do this in person, maybe. All right. So color temperature. How about color rendering? That's a little different. And color temperature and color rendering are not really related, although they typically come up in the same conversation. But they're different scales. So the color rendering is how well the light source reveals the true color of an object. And so we look at these two light sources, and you can only really compare color rendering with light sources that are the same or at least very similar color temperatures. Once you start changing the color temperature, it's not really a valid way to talk about color. You can't talk about color rendering. But so here's two 4,000 Kelvin light sources. And you can see down here, especially in these complexions, fairly dull complexions, the greenery looks a little flat, and these cars, if we didn't have that upper one, we'd say, well, it is what it is. But you see the one above, and everything pops a little bit better. So there's no, well, with color temperature, there's no right or wrong. I can't tell you not to use this in your, something like this in your hotel lobby, just like I can't say to not put this in your, warehouse. But usually you're going to find certain commonalities. But when it comes to color rendering, usually higher is better. We'll find some cases, I'll show you maybe a little later, where the highest isn't always the most appropriate for some reasons. There may be a point of diminishing returns, but generally there's no reason today where you'd be using any light source that's down here. Everything should either be good or excellent that you're specifying. And most LEDs don't generally come lower than 70, but you do need to watch for that. And if you're not careful, you may get 70 in a place where you really wish you had something in the high 80s. So, whoops, wrong way. So here we have different color temperatures and different color renderings. Here's a high pressure sodium light. Here's a mercury vapor light, lighting exterior sort of environment type stuff. And we can see how it's really changed, how some of these are very dull. And then we get into a high color rendering light source, ADCRI. Everything is equally bright and vibrant for the most part. So how does that work? Why do some things pop a little better than others under different light sources? Well, a light source can only reflect, or an object will reflect back only light that's in the source. So it's a kind of complicated little dance between the object and the light source. And so if I have a red apple and I shine a light on it that doesn't really have much in the way of red in it, I can't get that red light to reflect back. Just like if I have this red apple and I want to say, well, let's make our apples look blue. I can't do that. I can't shine there's enough blue light on here to make this look blue, because there's really no blue in the red, let's say, especially if it's a simple color. Sometimes we see objects that are very complex, and they could bring out different colors that we wouldn't otherwise see. But a simple red, it's only going to be red or variations on that. If we don't have red in the light source, we can't reflect it back, just like we can't reflect green back from the foliage. There's another thing that comes into play, and that's the ability to perceive that light. So we talked about the visible spectrum. Well, that's visible to the human eye. We're finding, this should come as no surprise, that the other creatures, insects and birds and who knows, our dogs and cats, they have different types of receptors. And so the human eye may see this bird looking like this, but other birds may see very different arrangement of colors. And then, of course, some percentage of the human population has a sort of a visual impairment, color blindness. It's not usually truly color blindness, but difficulty seeing certain colors. And so I think this is relevant if we're creating signage, wayfinding, wanting contrast to help people navigate spaces or read signs. You wouldn't want to have a sign that was basically a red background. Most color blindness occurs with red and green, so you wouldn't have a red background with green lettering to tell people where the exit was. You would have maybe a red sign with black lettering or white lettering that anybody could see that contrast. So you do need to keep that in mind when you're creating your spaces, or if you're doing like the edge of a loading dock or a stair rail or anything like that. Okay. So daylighting, we could do whole classes and seminars on daylighting, and it's a favorite topic of mine, but we're just going to touch on it a little bit, how it's used architecturally. So daylight can provide 5 important functions in buildings. Usable light for occupants, right? So we want windows so people can see around. Just putting in windows doesn't necessarily mean you have good daylighting though. A connection to the outdoors, right? People like to get a sense of, where am I? What's happening outside? And then a view corridor allowing eye muscles to relax, right? So if we're in small spaces all the time, the eyes are constantly straining to focus on things. Whereas when we get out, into a big field, an open space, the eye can relax because it's seeing at that long horizon. Daylighting can be a little bit messy when it comes to using light in interior architectural spaces, especially spaces that have fixed task areas. It's all over the place in terms of brightness. So here's our lux. We got a ton of it in the summer months and maybe not as much as we want in the winter months. It's also changing its direction. It's over here, then it's over there. It's high in the horizon, it's low in the horizon. It's sometimes not around at all. So there were times when the Illuminating and the Engineering Society was like, let's just forget about daylighting. We're just going to focus on electric light. And of course, that's simpler. It's much more predictable, but it doesn't take into account the fact that lighting is for people, and we want people to have good experiences in these spaces. And daylight is something that people crave usually, good daylighting. And then there's 4 types of daylight. One is direct sunlight. It's going to be quite exciting, but usually a little bit disruptive, especially in task areas. May be fine for atriums or concourses or places where people are walking through. Then there's just the clear blue sky, where it's just skylight, whether it's north, south, whatever. So it's daylight without sunlight. Then there's partial overcast. We see that a lot, where we have some daylight. And then there's overcast sky. So those are the kinds that you might be encountering. And again, we're not going to focus on that too much, but you can see it's a wide variation in terms of light levels with those. Keep this in mind though. So we were talking about spectrum before and perception. So obviously we have all the visual colors in the visible spectrum present in daylight. And we talked before about how, objects can only reflect light that is in the light source. So this would be an ideal light source for most applications. Can't always have it, and sometimes try to recreate it with electric light. So the other two things, I mentioned 5 things, and we talked about 3 of them. Another thing that we've found that people like is dynamic lighting. They don't like, we talked before about the indirect lighting and the cloudy day effect and how it's, constant shadowless light. People like dynamic lighting. We've evolved with that over millennia. And so if it's never changing, that's not necessarily good. And then of course, broad spectrum of light stimulation for the human physiology. So we're also finding that some of these non-visible portions of the spectrum are important. So yeah, I mean, the light can have very, very different qualities even at one moment. So here's just a east-facing mixed overcast morning, and you can see just the variation there just in that photograph. All right, another poll. Can you see that one, Armando?
It's a little blurry and transitioning. I don't see it yet, but I am going to go ahead and launch.
Okay, cool.
You're going to see. All right, we are talking about color temperature. Please select all that apply. Does color temperature tell us how cool or warm a light source is? Does it tell whether a light is bluish or yellowish? Is color temperature listed as CRI? Is it listed in kelvins? Or is color temperature dependent on color rendering? Awesome.
This is a tricky one.
Both coming in. I want to report, Eric, you are being extremely clear and awesome today. There are no questions being asked, but again, if anyone wants to further explore something, please go ahead and type it in the chat, and we'll address it live. All right, got most people voted already, so I'm gonna go ahead and close and share.
Sure.
We have 94% telling us tell us how cool or warm a light source is. 82% voted for tell whether a light is bluish or yellowish. I like it. 21% is voted for listed as CRI. Ooh, interesting. 82% voted for is listed in kelvins, and 15% voted for is dependent on color rendering.
Okay, well, good. I think most of us got it, and I'll be honest, this can all be a little confusing, especially if you're just starting out and there's a lot going on with these things. So, yeah, the A and B were both correct. CRI is color rendering index, so that's not color temperature. We do list the color temperature in kelvins. And it's not related or dependent on color rendering. They're separate things. Although, as I said, they often come up in the same conversation. Whoops, camera's backwards. Anyway, well, great. Appreciate the involvement there. All right, so let's go through some of these light sources real quick. So again, this is generic to any kind of light source. Now we're going to talk about some specific ones, and I'll kind of pick up the pace a little bit so we get through all this in a timely manner. So we do talk about light sources. I'm kind of a geek. I use the term light source, but you also use the term in the industry. They're called lamps. Even if they're LEDs, they're still a lamp, I guess. And then light bulbs. Well, I don't know. It's hard to know if here's an LED. I don't think I'm going to call this a light bulb, but this is an LED light bulb, so maybe maybe we're good on some of those. We do have different designations to describe the size and shape of light sources, regardless of whether they're LED or the historic. And some of those are going to be, we list the nominal wattage, we list the shape, T for tubular, G for globe, par. Where's the globe? Here's a big old globe. This is a G, G40, I think. Par type, MR. We list the diameter in 1/8 of inches. It's kind of an arcane thing, but that's how it is. And so here's an A19, A style, 19/8 of an inch across. And again, many of these designations are also used for LEDs, particularly in retrofit lamp types. So, this would be a LED, but it's a par 20, 28 of an inch. And you need to know that, because if you've got, say, a track head or a recessed fixture, is this going to actually fit in there? If it was designed for an incandescent or halogen par 20, I need to put a par 20 in there. If I buy a par 30, it ain't going to fit, be too big. So there we go. And then these shapes, as I've described, A style, PS, G for globe, T for tubular. Some of these are going to disappear and some will persist, and some are brand new, right? So with LEDs, we don't necessarily have to, this would be still maybe an A style or A equivalent, but it's a totally different thing. So yeah, some of the boundaries are changing, and that's good. All right, so with electric lights, they fall into 3 broad categories: resistive, discharge, and solid state. And the resistive are incandescent and halogen. Still see those in the stores, mostly halogen anymore. We see discharge, fluorescence, low high intensity discharge, and some of these others. And then solid state would be LED, OLED, and electroluminescent. It's crazy. I would normally teach back at, if this was 15 years ago, I'd have like 20 slides on incandescent lamps, and now it's boiled down to 1. So just bear with me. With an incandescent lamp, we have a globe, a glass globe. It needs to be glass because they generate a lot of heat. You'll see a lot of LEDs now that will have a similar globe, but it's made of plastic. It doesn't matter, not as much heat. But anyway, there'd be a filament in there, basically a piece of metal, gets heated up, starts to glow, and it starts to get so hot it incandesces. And then you have a base type. These base types are important, particularly if you're doing retrofit work. Medium base, candelabra base, mogul base. Those are different sizes. You got to make sure that the bases are consistent in size with what you're taking out to what you're putting in. And then you look at the spectral power distribution, right? So an incandescent lamp does have most of the colors of the spectrum, but as we probably know, they're very warm in color. Lots of red information in there, and not a lot of blue, but enough so that we can see blue reflected back. Fluorescent lamps. And so this would be what we call a continuous spectral power distribution. We look at fluorescent lamps, and just while we're on the subject, so here's a discontinuous spectral power distribution, little spikes here. Now these happen to correspond with our cone perception, right? So we see, we have cones that are red, green, and blue. So it's not all bad. We can still get pretty good color rendering, but anyway, they have a tube, usually glass, and there's a cathode in there. There's mercury, which some of you may have heard about inside traditional fluorescent lamps, usually a very small amount, but some. And then there's phosphors that coat the inside of this glass tube. So we create a plasma stream across here from there's a cathode here and a cathode there. And it's mostly ultraviolet light, but the phosphors turn that ultraviolet light into the visible spectrum. lots of different shapes with fluorescent. Again, an obsolete source now. You just basically need to know about them if you're removing them from buildings or you're finding something that's an equivalent with LED. And then high intensity discharge, HID. There's 4 types that we would see. Back in the old days, I would say, yeah, these last 2 are obsolete, mercury vapor and low pressure sodium, but guess what? They're all obsolete now. Metal halide, high pressure sodium. They would have a couple of electrodes here that would set up an arc, and then there'd be chemicals inside this arc chamber. It's like the surface of the sun in there. It's just insane. And so those chemicals start to really just throw off tons of light, tons of heat. You know, these would be 400 watt, 1000 watt. But it's definitely a point source. So we could control, we could throw that light, you know, 200 yards down to home plate, or light a parking lot from a 100 watt or 100 foot high mast, and we can put light all over the place fairly precisely. Discontinuous spectral power distribution. And you know, they have a thing called a strike time. So the problem with them is you flip the switch, and it might take 2 to even 10 minutes before you get usable light from them, which is a big problem when you're trying to do controls. Dimming, forget about it. So you know, not again, an obsolete light source. Range of spectral power distribution. So here's high pressure sodium lighting, you know, street lighting mostly. If LEDs had never come along, we'd be talking up this light here. This is ceramic metal halide. Really great color rendering properties. Excellent for retail, but guess what? Obsolete now. We're doing it with LEDs. All these light sources, the fluorescent and the high intensity discharge have a thing called a ballast. It's basically something that provides a starting voltage and current, and then regulates it so that it can operate predictably. LEDs, okay. You know, they're a solid state device. They're pretty flexible. Here's a pretty good size one. And you can get a sense from this that what we're looking at here is a cross section of this thing. So there's usually a lens of some kind. There's a little silicon chip inside there. We can run power into there. It's surrounded by a chunk of metal to pull all the heat out. So even though there's low energy, that energy is concentrated in a very small area. So thermal management is a big deal when it comes to LEDs, and getting that heat away from that little chip area as efficiently as possible is important. Poor to excellent color rendering. I would say probably good to excellent color rendering these days. It can be a white light, so lots of good things happening. You know, the thing about LEDs is we can make smaller fixtures if we want. You know, in the old days, the light sources were larger, physically larger. They also had a lot of heat associated with them, so the fixture had to be physically large to handle those things. Now we can make fixtures any way we want, pretty much. Higher efficacy, potentially better color, flexibility. They come on instantly. We can dim them easily. All kinds of great stuff happening with LEDs, as we know. Some LEDs come native, depending on their chemical makeups, in different colors. If you want saturated colors. But mostly we're in this class, and then for most of the projects you'll be doing, you want to think about white light LEDs. So there are 2 ways we can get white light with LEDs. One way is with the basic 3-color mixing. The primary colors of light are red, blue, and green. And we mix those, we get secondary colors, but we also get variations on white depending on the proportions of these primaries. Typically, when you're looking at a what we call 3-color mixing product, a fixture, it often has actually more. It'll be RGBA, so they'll put amber LEDs in there just to help with some of those warmer tones, or sometimes it'll be RGBW. They'll put just a white light LED in there to help get white, because even though you can get white with 3 colors, often it's best if you can augment that and help it out. But mostly what we are looking at when we talk about white light LED systems are what we call a blue LED, a blue pump LED doped with yellow phosphors. And if you know from basic light color mixing theory, when we do blue and amber, we get white. And so that's how it's mostly done. Kind of show you this little demo here. So here's a typical LED spectral power distribution. We can see a pretty good spike in the blue. They do blue fairly well. And then we can, depending on how much and what kind of phosphorus we use, we get the amber and reds. And so this spectral power distribution curve starts to look pretty good. If we think back to that daylight, it's not bad. So if we look at this LED here, it's a white light LED. Let's see if I can maybe do this. You can see that there. I won't blind everybody. So here's our blue white light LED. But if I take off the phosphor and shield this, we can see that this is actually, whoops, I can't do this right. This is a blue LED. There we go. And that's about as blue could be, right? It's just blue. And then I put the phosphor back. Here's my little phosphor chip. And I put that back on there. And I get back to my white light. So that is the magic of white LEDs. And we'll see 2 different types. So in this case, this is what we call a remote phosphor. You don't see this much. In fact, this light source, this by Philips, they pulled it off the market because people didn't understand it. They'd go to the store and say, I don't want yellow light, but they didn't realize it would be nice white light. But occasionally you'll see some recessed cans. I have an under cabinet light in my kitchen where if I turn it off and look at it, I get this strip of yellow that looks sort of like that. But when I turn it on, I get white light from it. So it's remote phosphor. But more often than not, they take the phosphor and put it kind of right on the chip. This is a giant one, but it also the same thing with smaller ones. All right. So just sort of like we talked about earlier, you know, like there's ways to have a kind of casual conversation about color, just like there's a way to have a casual conversation about beam spread. You can say, you know, flood or spot. That's not very precise. Just like warm and cool isn't very precise. That doesn't mean anything. And as we talked about earlier, with color temperature need to be fairly precise. And so we use numbers. We use 3,000 kelvins or, you know, 4,000 or 4,500 or whatever the number is. So you need to be a little careful when you see these descriptions, you know, natural or soft or bright. You know, bright, they're describing this color as bright, cool, bright white. Well, that doesn't tell us anything. Cool, maybe, or just here, bright white. So be careful with those and make sure you actually get the number. We have light sources that change, or rather luminaire types. And let's see if I can do this real quick here. Yeah, this is the one. Here's an LED. So if I turn it on once, twice, I get blue and then dim. And we'll do it bright, warm, bright blue, and dim, warm. Okay, I'm not sure how well that looks on the camera. But you couldn't do that before with before LEDs. You just couldn't do that with regular lights. All right, so I'm going to burst your bubble here. We talked about color rendering. Well, that's an obsolete system, but guess what? It is obsolete, but it's also the one we're currently using, and it's probably going to be around for a while. But we'll look at something that's probably going to come along. So color rendering is based on the average of the reflectance of 8 different pastel colors that they use in the lab. They take a light source, they shine it on these 8, and the reflectance back, they average that out, and it tells us, how well it reflects, pink, or how well it reflects, turquoise or purple. That's they average that, and it gives us the CRI. Sometimes it'll be called RA these days, our average. But what we're really interested in is, how does it look? And then when you do an average, that can be deceiving. You can have very good numbers in this blue area and pretty poor numbers in some of these other areas, and you wouldn't know that. You'd still have a high number. So, one thing that we were finding with LEDs is this R9, this saturated red. A lot of LEDs, weren't reflecting red back very well. And that's an important color when we talk about perception, whether it be for retail or looking at people's complexions, or a whole range of things. If we're not getting good reflectance back in the saturated red, people can look kind of greenish, or just it's not very good. So we're concerned with R9, and you'll see R9 listed. So it'll say the CRI is 80, the R9 might be, in the old days, the R9 might be 10, which is pretty poor. So anyway, you can see sometimes the R9 will be listed. So we have here's an LED chip that has RA of 97, that would be CRI, and the R9 would be 98. That's pretty good. Here's a compact fluorescent, CRI RA of 87, but the R9 was only 17, and that explains why a lot of times we have these compact fluorescents that were pretty high CRI, but I could tell there was something wrong with how it made my skin look. Anyway, so we want to look at that. Just keep that in mind, and as you get into more advanced in this topic, you'll be seeing this R9 listed, and you want a fairly high number. We also want spectral power distribution that's good. So CRI probably on its way out eventually. What's taking its place? TM30, the IS has come up with this new method. So instead of these, in this case, 8, sometimes as many as 15 chips, they're now using 99 chips to evaluate the colors. The problem I see personally with the TM30 is it's a very good, very refined method. I think it's going to be too complex for most people. And so even a specifier who is fairly adept has to communicate to their client or the buyer what these numbers are, or about the light source. And I just think it's going to be tricky to do that. But the TM30 is the method that's emerging, and again, could do an entire class just on that. And in fact, there are classes on that. So LED shapes, especially with the screw-in products, come in a whole range. And then with the chip types, there's a whole range, whether they be linear, point sources, or larger radiant surfaces. You do need to be careful when you're taking out an incandescent, or rather a one type of light, say in this case it would have been a metal halide, and putting in an LED. You can get some kind of unexpected patterns. This is in one of the, I guess, transit tunnels in Seattle. this could have been a disaster if it was a certain type of space. As it is, it's just kind of unusual and unique. But it doesn't always hurt to check before you go. And as with fluorescent and high intensity discharge, LEDs have a power supply. We call them drivers, and having a knowledge of the drivers is important for success. They just are used to operate. So as far as dimming goes, especially in the old days when you're dimming an incandescent load, it's just a simple resistor. So it's easy to translate that in terms of communication. But with solid state lighting, we've got the driver, which is a solid state device. Then we've got the LED, which is a solid state device. They all require language, and then there's the dimmer itself. All that has to be consistent, and it's very difficult to get that because these are often done by two different manufacturers, and then here's yet a third manufacturer. Not so easy. So we look at compatibility charts, especially for screw-in type products, but that would be for drivers as well. This goes on for 40 pages, and it's constantly changing. So it's a little bit tricky. And then of course there's this dimming protocols that you're using. Is it 0 to 10 volt? Is it Dolly? Is it some sort of proprietary platform? Is it a DMX? So what you really need to do is look at the literature, make sure there's consistency when it comes to dimming, and then double check and get some samples and make sure that's actually going to work. Flicker is another thing that had sort of gone away with high frequency ballast, but now with LEDs, potentially it's back. Sometimes it can be okay. It can be mildly annoying, hugely annoying, or disastrous. So we see holiday displays and maybe they chatter a little bit, maybe a little bit of flicker, probably not a big issue. But if you've got a music hall, let's say, and you're dimming things down to say 70% or 30%, and it starts to flicker, that's a deal breaker. You can't have that. Or in a restaurant, not going to work. So you do need to make sure these things are not going to flicker. OLEDs, organic LEDs. So that's a sheet of luminous material. It uses a similar process as LEDs, but it uses a different substrate. And I don't know, I like to sort of quip that OLEDs are the light source of the future and always will be. They've been around for a while. They are, interesting. I think they have their place in creating visual interest in architectural environments, but in terms of just doing the heavy lifting of lighting big architectural spaces, they just don't have some of the specifications that we're seeing. Now, these numbers are changing. The OLEDs are improving. I've talked to people, who are manufacturers of OLEDs, and this is all, the curve is good in terms of improvement, but it's not keeping up, with traditional LEDs, if we can call it that. So we're probably not going to be seeing them as much, but again, they do have niche applications, maybe task lights, maybe art pieces in big spaces. All right, so once we start to look at things like this, is this a light source or is it a luminaire? So let's look at luminaires. Going to try and keep up the pace here, but basically a luminaire is a complete lighting unit designed to safely hold the light source in the space, direct the light in the intended way, and provide glare control and shield the components that are not intended to be seen. So you don't want to be looking into it, seeing sockets and screws and stuff necessarily, unless that's the intention. Sometimes they're called light fixtures, and in fact, they're frequently called light fixtures. And depending on which side of the Atlantic you're on, they're also sometimes called light fittings. So if you're working with somebody from Britain, they might talk about fittings. So the classic luminaire breakdown would be, you know, the source, particularly with LEDs, the light sources are baked right in usually. Baluster drivers, reflectors, refractors, shielding, housing, etc. Light distribution. This gets a little bit into sort of a design class, but really effective lighting design means putting light where it is wanted and needed and eliminating it where it's not wanted or needed. And part of that process, of course, is having a luminaire that's going to have the proper optics to perform that task. So we look at distribution. You know, you can have similar luminaires. This luminaire could provide all these different light distributions. And so you would pick the one that's most appropriate, but in a given building, you might have the same profile, but you're getting different kinds of lighting from depending on the space and its location. So we have reflectors. You know, even with LED, we have reflectors, and they can shape the light, and there's different kinds. The basic type, you know, of specular mirror-like reflector, angle of incident equals angle of reflection. So we've seen that before, and that's a tool. But bear in mind, we've seen people say, well, we're going to use specular reflectors, and we're not going to have, how do they put it? We're not going to see the light, the LEDs, but you look at it and it's reflected right there. It's like in a mirror. You can't just look straight at it, but it's you're seeing it. So be a little cautious. This is where it always helps to actually see a sample of your product. And then there's a diffuse reflector, right? So that's where the light hits it and comes off in a diffuse omnidirectional way. And that can be quite appropriate for many applications too, to really cut down on any glare potential. But more often than not, we're seeing what we call sometimes semi-specular, where the light hits it. It still comes off in the direction we want, but it's diffused a little bit. So we have directionality. And then there's just infinite variations on those. So then we have some reflector shapes. So here's our light source for a basic parabola or parabolic reflector. We're going to get light out in a sort of a coherent pattern. And then we may want to shape it or diffuse it with a lens, perhaps. And then we have spherical, where things converge. The other one that we'll see a lot is ellipsoidal. They have two focal points. So here's our light source surrounded by our reflector. The light will reflect back. And then our focal point is, we have a secondary focal point outside the reflector. And that allows us to have very small apertures sometimes for our fixtures, because the light can converge and go out of the fixture and then spread again, and we can shape it with lenses. And then there's asymmetric reflectors, right? So sometimes we want to put more light energy down, farther away from the fixture. And the reason for that is, say here's our wall. Let's say this is a wall. Here's a wall wash type fixture. This might be the distribution pattern for that, and it's seeing more light coming down towards the floor. Well, the reason is because we don't need as much light energy up here because it's closer, and there's a real connection between distance and intensity. The farther a light has to go, the dimmer it gets. So we want to put a lot of light down here so that it looks uniformly lit. Shielding and refracting, we have lenses. We want to block the image of the light sources. We want to distribute the light in specific ways many times. So we have different types of lenses and transmission. Here's a direct spread type lens, so the light comes through it. It breaks up a little bit, but it still maintains its direction consistently. Then we have a diffuser, again, a little bit like the diffuse reflector. It comes down and then it just very diffuse, goes in every direction it could possibly. Sometimes we want to selectively allow transmission, and we want certain parts of the spectrum to be sent away. That was especially true with dichroic reflectors. When we had halogen light sources, we could send a lot of infrared energy. The heat energy would get reflected, and only the visible portion would come through. And then we want absorption for different reasons. Other times we want to change the direction, right? So we want the light to come in a certain way, but then we want to bend it, but it still needs to stay in a nice coherent beam. And so here we have different types of lenses, and they'll create different degree beams, just like we had with our light sources. We could have a narrow beam, a wide beam. This would be a Fresnel type lens with various little prisms cut into it now to diverge or converge the light. Other times we're just doing something as simple as shielding direct view of the lamp. Bear in mind though that say here's our light source, is a recessed can. This would be a troffer type fixture like this one. You want it, and here's our side view of a linear fluorescence, but this would be true even with LEDs. So here's a case where these are parabolas. So we don't want to just have a flat reflective surface there, because then we'd just look up and we'd see a reflection of the lamp. It's got to be a careful parabola so that we're shaping the light, shielding the light, and not creating glare. Okay, I think we got another poll.
Beautiful, great, and I want to say from before, awesome show and tell on the different LED sources and codes. It's great to see live.
Oh yeah, semi-live.
All right, going back to a couple of slides. Poll on reflectors. Select all that apply. Reflectors can be either specular, diffuse, ellipsoidal, incidental, or asymmetric. Thank you for those that are voting already. So again, fixture reflectors can be specular, diffuse, ellipsoidal, incidental, and or asymmetric. Okay, it's a good amount of voters coming in. Thanks a lot. 3 more seconds. All right, gonna go ahead and close this here. Let's go ahead and share. 73 participants voted on specular, 73% as well on diffuse, 65% voted with ellipsoidal, 8% voted for incidental, 73% voted on asymmetric.
Excellent. Well, great. Yeah, they were the only one that really was I kind of just sort of made up was D, the incidental, although you could be confused because there's incident light, the angle of incidence equals angle of reflection. But yes, so that was really, D was kind of a little bit of a trick there. But the others were types, so excellent, well done. Let's just plow ahead. So when we want to categorize luminaires, we also want to categorize them in terms of how the light exits the luminaire, how they distribute the light. And a lot of luminaires that we used architecturally are direct, and that means that 90 to 100% of the light comes directly out of the luminaire into the space onto the tasks. This is a side view of a troffer. Indirect luminaires, so here's a side view of in this case, a linear pendant, but it could be even this little round guy here. 90 to 100% of the light comes directly up. And you could have an indirect, sconce type as well. I mean, these don't have to be pendants. They can be bracketed to the wall as well. So indirect luminaires, one thing that we try to do with indirect luminaires is, unless there's a reason, you want ideally the light to come out. Here's light coming out, side view, and it touches and then starts again. Usually you don't want big gaps between the light from one to the next. You can create lots of patterning on the ceiling, but you might want that, but just, and that would be a function of mounting height sometimes, or getting different kind of optics. I included this slide. It's crazy. I went into a building a couple years ago, and this is the entry lobby. And walk in this door, you might go, I think there was some doors there and just elevators and just different things. It was crazy. So here's all this direct lighting, and this is all indirect lighting. And I swear I'm standing right in the same spot. I turn one direction, I take a picture, I turn around, I take another picture. It almost looks like there were two design teams that were at war with each other. And they said, okay, you get the first 30 feet of the lobby, we get the last 30 feet. Because this is literally the same space. I just turned around. Anyway, but I thought it was a good case study, and indirect and direct. There we go. Although this isn't totally direct, you can see it, but it's a lot of the light is bounced off the wall. And that's how it really creates some lighting in the space. But most spaces, most of the times you're going to see direct, indirect, or indirect, direct. They have lots of different ways to categorize these, but some portion of the light is going to go up and some is going to come down. And depending on where they are, how they're located, what you want, you're going to use those. And then there's omnidirectional, right? Where the classic would be these big spheres. This is a relatively modern building, so but it sort of has that 60s look. But you can have a big chandelier where even if these weren't balls, it would still be putting out a big diffuse amount of light, generally lighting the space. So it's rare to find a truly omnidirectional fixture. So even like these balls here have a little bit of drop off directly above the fixture. And then adjustable, whether it be for interior or exterior, where you're adjusting the light, you're able to shine it different directions. Those can be very helpful. They can also be tricky if you don't have enough mounting locations. You try to shoot the light too far away, either it'll drop off or you will start to create low angle glare. And I always get the question, again, this gets more of into design class, but let's touch on it briefly here. How far out should I mount the fixture? So if here's our artwork, let's say, or whatever we're lighting, a display case, here's our basic center beam. You want to think of about a 30-degree-ish, no more than 45-degree, independent. So here's our mounting height. But if our ceiling height was different, this would just go up and up and up, and we go out and out further from the wall. So when people say, how far out should I put the fixture to get good angle, I say, well, what's your ceiling height or what's your mounting height? It's always the next question you have to ask. Wall washing. We have fixtures trying to uniformly light the wall while grazing. Where we're coming down, we want to create some drama, usually define the space. So when we look at catalog cut sheets, there's a lot of ways to look at them. And I think we're going to try and breeze through this because it can be fairly detailed, but some of them have just simple data, the name of the fixture, general shape, some dimensions, some options, but not really a lot here in the way of what we'll call photometrics. And that's fine for many decorative types of fixtures. There may not be photometrics. There might, you never know. Other times you see a cut sheet and it's just crammed full of information, right? So here's our recessed fixture, and you have all different kinds of options here, ordering codes, spec sheets, dimming capabilities, you name it. So all these things would be part of the specifications for this last fixture cut sheet we just looked at, just this little recessed can. One of the things that they'll often do, which can be helpful, so you're looking at all this data and they say, they'll often give you an ordering example. So let's say for instance, for this fixture, the example might be 3131, and in fact, it's 3131, W wet location, but it might have been W wet location or non-wet location, which would just be normal damp location. So maybe eliminate that W if it was without the wet location. B1, or it could be these other types of bevels, different lens types, a whole range of different things. And then we get into the housing type, because usually you're ordering trim for recess fixtures, housing and trim together. So there's the housing code, but then again, a whole range of things with color temperature, color rendering, beams, you name it, dimming drivers. So it can get fairly complex. Photometric data can be, fairly comprehensive. You'll see color temperature. Depending on the color temperature, we'll have various lumen packages. So you want to be a little bit aware of that. You may have different, here the similar color renderings, but that can change as well. Then we'll look at candela distribution. Sometimes it's as simple as just a side view. So here's our fixture. We know that most of the light comes out this way, but there's going to be a little bit of light coming out the back. That could be helpful. It could be a problem. Here we see a very narrow beam of light coming out, almost no light energy coming out past 10 degrees really. So this is really just a narrow beam. And other times we're looking at different orientations, right? So here's a pendant, or actually this could be a ceiling mounted linear fixture. And we know that on the often it's X and Y axis. So on the perpendicular axis, we're going to have one distribution, usually symmetrically. They'll just give you one side. But if we go along the axis, we're going to have a different distribution. And so that's good to know for certain fixtures. How do we get all these numbers? Well, we have two big pieces of equipment. Here's our integrating sphere, where this would be a 9-meter sphere, where we could put, or a 3-meter sphere rather, where we could put our light source, or sometimes even a whole luminaire, depending on the size, inside there, and we can look at the overall lumen output. And then here we can look at the zonal distribution of that, how it's coming out in different zones. And we take our light fixture, mount it here as a big old mirror, and this arm, it goes around at very precise angles, and it takes angular measurements from, then it'll get hundreds of data points. And, it has to be automated like that, because here's just one fixture, and this is all the different photometric type data that you can have for that. So it just goes on and on. But we talked earlier about a relationship between color temperature, color rendering, and lumen output. And we can see here, we've got, so if you go back to this basic high bay style fixture, here's our 30,000 lumen example. Well, at 4,000 kelvins, at 70 CRI, we get 29,000 lumens. And we're thinking, wow, that's pretty good. But let's say we were using this maybe in a food court, or maybe I don't know, airport concourse, high atrium type area, where maybe you're not going to really see the fixture, but we want to blast a bunch of light down there. And we're thinking, well, we want better than 70 CRI, and we don't want 4,000 kelvins, we want warmer. So we have 3,000 kelvins, and maybe we want 90 CRI. Let's say it's a big retail space, but not a Home Depot, like maybe a Costco or someplace. Well, now we only have 18,000 lumens. That's a pretty big difference. We go from 125 lumens per watt to 80 lumens per watt. But you know, that may just be the cost that we have to have. We can't say, well, too bad. We have to have 125 lumens per watt, so we're going to put it in our food court, and the food's just going to look bad, and that's too bad. No, I mean, sometimes it's the cost of doing business. So, but just be aware that your lumens could go down considerably, or they could go up if you needed more lumens, and maybe it didn't matter. You know, why would you need 90 CRI maybe in a warehouse? 70 should be plenty good for people to read labels on the boxes. So anyway, again, that relationship between color rendering and lumen output, if we have in this case, sometimes we'll have multipliers. So here we've got, if we have 2700 kelvins, very warm, we take our baseline lumens, multiplier of 1, and now we have to multiply it times 0.94, a little less lumens. Or if we had our baseline 3500 kelvins lumens, multiplier of 1, if we go to 4000 kelvins, same CRI, now we multiply times 1.06, and we get a little increased lumens. Okay, so luminaire efficiency. Usually in the old days, we would see a fixture and we'd have an efficiency rating for that fixture. So here's a case where we've got 1800 lumen, a compact fluorescent fixture with 4 1800 lumen lamps. That should be about 7,000 lumens or so. And maybe we're replacing that with a couple of LED fixtures. And we're looking at, like, you know, this one's 2,500 lumens. This one's barely 2,000 lumens. How can we possibly replace that? But look, if we look at our luminaire efficiencies, here's our compact fluorescent fixture. Its efficiency is 37%. That's right. Over 60% of the lumens from those compact fluorescent lamps never make it out of the fixture, never make it past that lens. So we're really only getting about 2,600 lumens. So that changes our calculation considerably. So it's really not 7,200, it's 2,600. So now these don't look quite so bad. And let's look, but we're thinking, well, this one's going to give us more light than that one. And maybe this one's a little cheaper. We have, you know, let's just look. So here's this one. We're going to look at it, the fine print a little more carefully. And guess what? We look at this fixture, it says standard 3500 LED source lumens noted. Source lumens. That means it's the lumens from the LED chips, not from the fixture. So we don't really know what the efficiency of that fixture is, but we also don't know how much light we're actually going to get out. It's listing 2,500 source lumens, whereas this other fixture lists delivered lumens. That means they actually measured the lumens of the coming out of that fixture. So you have to be careful of whether you're looking at source lumens or delivered lumens. And if you ever see this thing called a lighting facts label, that would be luminaire lumens that they're listing. And if they change anything, like the lens type or the finish on the, you know, where it goes from brass to chrome, you have to run the photometric test again and get a whole new photometric report. Okay, I think this might be one more poll. And I'm running out of time.
And we will be efficient.
Maybe, do you want me just to read through this one, Armando?
Yeah, go ahead.
Yeah, let's just do this one. So luminaire efficiency is, and I'll just read them and we can kind of do it together. Not always relevant with LED fixtures.
Eric, do you mind going one more slide? I think we don't see it.
Oh, sorry. Do you see it now? Oh, well, maybe, why don't you put the poll up? And I'll just talk through it then. I think that maybe the poll, you don't see it.
It is up.
Okay, great. Yeah, so luminaire efficiency is not always relevant with LED fixtures, and that's that's true, because sometimes when you see delivered lumens or luminaire lumens, that tells you that's how much light's coming out. So you don't really care how efficient the fixture is. Dependent on CCT, not necessarily. Lumen output can change depending on the color temperature. It varies depending on the components. That is certainly true. If you change the lenses or anything like that. Measured in foot candles, no. Is the percentage of light out of the fixture relative to the light from the source? And that is true. So yeah. Here's a little image here that might be interesting. So we've got this retrofit here we did. This used to be incandescent lamps. And they went and upgraded to LED, but the problem was they didn't realize what they were supposed to be lighting was this piece of artwork here. You know, sometimes it doesn't do any good if you're going to do a retrofit that doesn't actually perform the function. You need to be careful of that. All right. So here's a little luminaire checklist, and I think we're getting close to the end here. So I think I'm just going to maybe, I'll go through these basic categories and let you kind of look through this, but you want to ask these questions when you're looking at any kind of light fixture. You know, will the distribution put the light where I want it? And then, as we saw in the case here, not really. What light source does it take? You know, I'll let you read through these things. Checklist: is the frame durable enough? Is it made out of steel? Is it aluminum? Is it plastic? You know, is the finish durable enough? Will it handle the environment? Is the lens durable enough? Is it going to start melting away over time? Are there any special power requirements that I need? Transformers? Is it 277 volts? Compatibility with the various components. What about the warranty? You know, this company had 10-year warranties on their stuff, but they're out of business now. So I'm not sure what good that does you. So you need to be careful of that. Environmental factors for where I'm going to be putting the fixture. So the last quiz that we had, Armando, I think you can bring that up.
All right, I have it over here, and it is the most effective luminaire, and select all that apply, is energy efficient, has appropriate color qualities, puts light where it's needed, has low operating costs, and is controllable.
And the answer is all of the above.
Like everyone who's voting, that's pretty much what everyone's going with, so I like it.
Yeah. Yeah, so, you know, really, you want to hit all those boxes. And so, right. Well, I appreciate you guys hanging in there. This is, again, I wish we had more time. If there's any questions, feel free to give me a call, or I'll be hanging around a little bit if anybody has any burning questions. But like I said, either call me or email me. Thank you very much. Armando, take it away.
Sounds great, Eric. If you can advance to the next slide, please.
So you're looking at the upcoming online events?
Oh no, we still see your beautiful dog.
Oh really? Because I'm okay. Let's go back one. I go forward one. No, because I'm seeing online events, upcoming events rather.
Upcoming. Well, I don't see it, but I know it by heart, so I'm gonna go with them. We have a great series coming up. Lighting Design Lab. We're touching on building electrification topics, code updates, and in September we're gonna have. Oh, there we go. Now I see the slide change. We're gonna have a code update from the 2018 Washington and Seattle energy codes. So on the 14th, we're gonna be discussing building envelope. On September 21st, we're going to talk about the updates to code on lighting. And on September 28th, we're going to be talking about updates to code on HVAC. This code was put in place earlier this year. And we know some trade allies, contractors have already had some experience looking to meet code. So we have a great presentation by Seattle's Department of Construction and Inspection's own Dwayne Johnlin, working alongside industry partners. And they're going to be doing some great discussions as to how to break down code and what designs, products, and strategies are available to meet and exceed the requirements. Also, on the 15th and the 16th, we are also part of the code series. We are going to be discussing commercial.
Armando, I think I lost you. Can you, I'm not hearing you. But, well, check our website and look for these upcoming events starting mid-September. And let's see. And I would just say, come contact us, contact me if you have questions about anything. And thank you very much. Been a lovely audience, and we'll do it again sometime.
Hello.
Hey, Armando. So,
did you finish the webinar? I just got a lightning strike and took out a router.
oh my God. Okay. No, I did sort of, yeah, you kind of just disappeared. Wasn't sure exactly how to, I thought I stopped the recording, but who knows, we may still be live. I'm not really sure. I did thank everybody and I went through all the rest of the slides.
No, yeah, thank you very much. If you want to report, yeah, this is my connection. But no, if you thanked everybody, everything that you need to do, yeah, just close out on the end. It should be good to go.
Okay, fair enough. Oh yeah, leave webinar, I see.
All right, you as well. Have a good one. Bye.